Alex Krzyzewski, Ilya Sutskever, and their advisor Geoffrey Hinton, one of the godfathers of deep learning. Their model? AlexNet. 8 layers deep. Think of it like teaching a child to recognize a cat. First you show them lines. See these strokes? Then textures. Feel that? That's fur. Then shapes. Ears are triangles, eyes are circles. Then parts. 2 pointy ears, whiskers, tail. Finally, all of that together, that's a cat. AlexNet learns the same way. 8 levels to build up from lines to cats. Deeper networks existed before, but they weren't winning ImageNet. Handcrafted features still dominated. AlexNet proved, scale up depth with GPUs and you win. Krzyzewski trained it on 2 NVIDIA GTX 580 GPUs in his bedroom at his parents' house. When the results came in, it turned out they won by 10.9 percentage points. Top 5 error, 15.3%. Runner-up, 26.2%. Is that gap normal? No. In 2010, 28% error. 2011, 26%. Progress was slow. Then AlexNet, 15.3%, jumping further than the previous 2 years combined. The field was shocked. Why didn't everyone else use GPUs and deep networks? Because neural networks were considered old-fashioned. They'd been tried in the 80s and 90s, and hadn't worked well enough. Most teams used handcrafted features, edges, textures, patterns they designed manually. The field had moved on, or so everyone thought. Hinton's lab at Toronto decided to dust off the old idea. Krzyzewski was an expert at using NVIDIA's CUDA to make graphics cards train neural networks, something almost no one knew how to do at the time. They saw what others didn't. The message was clear. Deep learning works. For 20 years, neural networks were considered a dead end. AlexNet proved, scale it up, give it data and GPUs, and it gets better. But AlexNet only recognized images. What if we wanted to create new ones? 2013. Diederik Kingma and Max Welling published a paper on something called a variational autoencoder, VAE. The idea: compress an image into a small code, then reconstruct it, like a zip file for images. 10 megabyte photo becomes 200 kilobytes, essence preserved. You tweak the code, you get a slightly different image, it works. But the images? Blurry, like a slightly out of focus photo. You can see what it is, but fine details are soft. Text becomes hard to read, hair looks painted on, edges smudge. Why? The model learned from thousands of cat photos. Some cats have whiskers pointing left, some pointing right. When reconstructing, the model plays it safe. It draws whiskers somewhere in between. Soft, averaged, blurred. Same with edges, same with textures. The model minimizes error by averaging, safe but blurry. Then comes 2014. Ian Goodfellow, a PhD student under Yoshua Bengio at the Université de Montréal, is at a bar with friends discussing how to generate realistic images. Friends are skeptical of his 2 networks competing idea. Goodfellow goes home, codes it at night. The idea worked remarkably quickly. He calls it a Generative Adversarial Network, GAN. Here's how the competition works. The generator creates fake images from random noise. The discriminator tries to detect them, real or fake. Generator gets better at faking. Discriminator gets better at detecting. They push each other. Eventually, generator is so good, the discriminator can't tell. 50-50 guess. The results? Sharp. Revolutionary for 2014. GANs becomes the future of generative AI. By 2015, everyone's working on them. Universities, MIT, Stanford, Berkeley, companies, Google Brain, NVIDIA. Better faces, better resolution, better control. The path forward seemed obvious. But there was another idea, one that almost no one noticed. March 2015. Jascha Sohl-Dickstein, a researcher at Stanford, publishes a paper with a physics-inspired title, Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics. Stick with me. The idea is counterintuitive. Take an image, gradually add noise to it, step by step, until it's pure static. Like the TV snow you'd see at 3 a.m. when all programs ended. Then, train a model to reverse the process. Start with noise. Remove a little bit. Remove a little more. After hundreds of steps, you get an image. But wait, how does a model know what to create? You train it on millions of real images. The model learns the patterns. What cats look like, what faces look like, what textures appear where. Then, when you start with noise and remove it step by step, the model follows those learned patterns. It's not creating a specific image, it's sampling from the distribution it learned. It's based on how particles diffuse in physics. Heat spreads through a metal rod. Ink disperses in water. Drop of food coloring in a glass. Watch it spread out, never unspread. All governed by the same math. The paper is elegant, the theory is sound, but there's a problem. It works too slowly. Generating one image takes thousands of steps, impractical for real use. The paper gets a few citations. Some researchers find it interesting, but the world moves on. 2016 to 2020. GANs dominate. StyleGAN generates photorealistic faces. BigGAN creates high-resolution images. Training it required 512 Google TPUs. Estimated cost, tens of thousands of dollars, likely around 60,000. Progress is fast, but GANs are fragile. Mode collapse. The model generates the same thing over and over, like an artist who discovers critics love their portraits. They stop painting landscapes, still lifes, abstracts, just portraits, over and over. Behind the scenes, infrastructure is maturing. GPUs get faster, frameworks get better, datasets get bigger, and a few researchers keep thinking about diffusion. June 2020. Jonathan Ho, a PhD student at Berkeley, publishes a paper with Peter Abil. The title, Denoising Diffusion Probabilistic Models, DDPM. It's still based on Sohl-Dickstein's idea from 2015, but Ho makes it work. Better training objective, better noise scheduling, better architecture. The key change, instead of predicting the final image directly, predict the noise at each step. The results? They beat GANs, not in speed, in quality, in diversity, in stability. GANs are fast but unstable. They collapse. Generate the same thing over and over. You tweak one setting, training explodes. Diffusion models? Slower but reliable. Stable training. Predictable scaling. The AI research community notices something remarkable. DDPM beat GANs on quality metrics. FID score, inception score. Papers start appearing. Google, OpenAI, universities. Everyone's experimenting with diffusion. But there's still the speed problem. 1,000 annoying steps to generate one image? That's minutes, not seconds. GANs? One forward pass. Done. Less than a minute to sample 50,000 images. DDPM? 20 hours for the same. 1,200 times slower. For consumers? Unacceptable. The breakthrough needed one more piece. December 2021. Robin Rombach and a team from Ludwig Maximilian University of Munich publish high-resolution image synthesis with latent diffusion models. The key insight: don't run diffusion on pixels. Run it on compressed representations. Think of it like this: carving a statue from marble. Slow, painstaking. Every mistake costs you hours of work. But what if you worked with clay instead? Clay is soft. You shape it quickly. Make a mistake, smooth it out, try again. Faster, easier, forgiving. That's what latent diffusion does. Remember VAEs from 2013? Compress the image first. 512 by 512 pixels, 786,000 RGB numbers, like carving every color variation in marble. The VAE resculpts into clay, 64 by 64, with 4 learned channels, not red, green, blue anymore, but compressed abstract features, 16,000 numbers, 48 times smaller, same image, denser medium. Run diffusion there, work with clay, not marble, then decode back to pixels. The result? Significantly faster, at least 2.7 times speedup, and crucially, it runs on consumer GPUs, a GTX 1080, 8 GB of VRAM instead of 100. This is the game changer. April 2022. OpenAI releases DALL-E 2. The name is a pun. Salvador Dali meets Wall-E. The tech? Diffusion models guided by CLIP. CLIP is another OpenAI model. It connects text and images. You type an astronaut riding a horse in space. CLIP understands what that means. Diffusion generates it. The model learned from millions of image caption pairs scraped from the internet. It knows what astronaut looks like, what horse means, what space implies. The quality leap is staggering, photorealistic, compositionally coherent, controllable. But DALL-E 2 is on a waitlist. Researchers and select testers only. And then comes July 12, 2022. David Holtz launches Midjourney. No academic paper, just a Discord bot. And it goes viral. Artists flock to it. The aesthetic is distinctive, painterly, dramatic, cinematic. Twitter fills with Midjourney art. This is the moment normies hear AI art. Not researchers, not engineers, graphic designers, illustrators, hobbyists. Midjourney proves there's a market. 1 month later, August 22nd, 2022, Stable Diffusion is released, built on Rombach's latent diffusion paper, released by Stability AI, LMU Munich, and Runway ML. But unlike DALL-E 2, unlike Midjourney, it's completely open source. Downloads awaits. Run it locally. Modify it however you want. An ecosystem explodes overnight. ControlNet lets you guide composition with sketches. LoRa lets you fine-tune on custom styles. DreamBoost trains on your own face. All built by the community. In the first 2 months, 10 million users. October 2022. Jonathan Ho, the same researcher behind DDPM, publishes Imagine Video with Google. Not images, video, generated from text using diffusion. The quality is rough, the resolution low, but the direction is clear. Diffusion isn't just for still images anymore. 2023, 2024, the product explosion. Midjourney version 5, photorealistic. Version 6, even better. DALL-E 3 integrated into ChatGPT. Stable Diffusion XL, higher resolution, better prompt understanding. Every week, a new model. May 2024. Google announces Veo, text-to-video, diffusion-based. Today, 2026, you can generate 8-second clips, or chain up to 20 of them together, about 2.5 minutes total. Midjourney has over 21 million users. Diffusion powers tools everywhere, from Photoshop's generative fill to open-source communities, video creation, image editing, 3D generation. But they still struggle with some things. Hands, fingers, complex anatomy, not a bug of one model. A limitation of learning from patterns, not physics. Still, diffusion won. From a physics paper in 2015, to consumer products in 2022, to everywhere in 2026. 11 years. But the revolution isn't over. Researchers are working on flow matching. One-step generation instead of 50. 3D diffusion for objects and scenes. Jan LeCun is pushing JIPA to predict rather than generate pixels. Real-time video generation. We went from noise to images. What comes next? In the next video, we'll go deep. How does diffusion actually work? The math, the intuition, the code.